This is a video about a single simple rule that underpins all of physics. Every principle from classical mechanics to electromagnetism, from quantum theory to general relativity, right down to the ultimate constituents of matter, the fundamental particles. All of it can be replaced by this single rule. Feels like we're approaching spooky territory.
We're approaching spooky territory, I hear you, and I agree.
It may in fact explain the behavior of life itself.
I think I'm stuck in some classical mindset where, to me, the local picture, differential equation way of thinking about the universe, that's really what's going on. But I fear that I have it exactly backwards.
And it all starts with a simple problem. If you want to slide a mass from point A to point B, what shape of ramp will get it there the fastest? This is known as the problem of fastest descent.
You know, common sense, you might say, take the shortest path. Straight line from A to B.
But if you bend the ramp down a bit at the beginning, well, the mass accelerates to a higher speed earlier, so even though it travels slightly farther, it travels faster and beats the straight ramp. So the question is, what shape provides the perfect balance of acceleration and path length to minimize travel time? According to Galileo, it was the arc of a circle. He showed that this is faster than any polygon. But is it the fastest? Nearly 60 years later, in June of 1696, Johann Bernoulli set this problem as a challenge to the best mathematicians in the world.
Mainly because he's a big show-off, and he wants to show that he's better than all of them.
He gave everyone 6 months to come up with solutions, but none were submitted. So Gottfried Leibniz, a friend of Bernoulli's, persuaded him to extend the deadline to give foreigners a chance.
And I think Newton was probably the intended target, because everybody thought of him as the best, and so Johann would have wanted to show that he was better than Newton. He was no longer really active mathematician or physicist. He was working as the warden of the mint, like a big high government position.
And on the 29th of January, 1697, Newton returned home after a long day at work to find Bernoulli's challenge in the mail. Irritated, he wrote, "I do not love to be dunned and teased by foreigners about mathematical things." But the problem was too enticing, so Newton spent the rest of the day and night on it, and by 4 a.m. he had come up with a solution, something that took Bernoulli 2 weeks. Newton submitted his solution to the journal Philosophical Transactions.
He sent his solution there but didn't sign it, and Johann Bernoulli, after seeing the solution, is alleged to have said, "I recognize the lion by his claw." You know, that, okay, you don't need to sign it, Newton. I can tell who you are. Who else could give such a solution?
And while overall Newton dominated Bernoulli, in this instance, Bernoulli's solution actually outshone Newton's.
I could see why Johann Bernoulli wanted to challenge everybody, because he came up with a really clever, I would say like a truly creative, beautiful solution.
To do it, he took inspiration from a problem faced by ancient philosophers. How does light travel from one place to another? This was contemplated by Hero of Alexandria in the 1st century AD. He realized that in a single medium like air, light always follows the shortest path. A consequence is that when light reflects, say, off a lake, the angle of incidence is always equal to the angle of reflection. Any other path between the start and end points would be longer. But when light goes from one medium into another, like from air into water, it bends in a peculiar way. It refracts, and it doesn't follow the shortest path.
If you've ever dropped something at the bottom of a swimming pool and you look for it through the water, if you put your hand in there, it's not necessarily where you think it is, because the light has bent away from the flat surface.
So what is the guiding principle here? Well, over the next 1600 years, people slowly figured out that the sine of the angle of incidence divided by the sine of the angle of refraction is equal to a constant, n, which depends on the nature of the two media. This came to be known as Snell's law,